Hello, welcome. This is part 3 of a 3-part series where we try to predict who's going to win the NBA MVP each year. And this part is where we do the machine learning part and actually make the predictions. In part 1, we did web scraping to get the data. In part 2, we cleaned up the data. And that leads us to part 3. You don't need to have watched parts 1 and 2 to actually follow what's going on because we'll start with a CSV file. But if you do want to go back and watch, I will include links, both in the video description and throughout this video. With that said, let's go ahead and dive in. So we're going to be using Jupyter Lab as our interface for actually exploring this data and doing some machine learning. So you'll notice there's a file called player MVP stats. I'm going to open that in the CSV browser. And you can see that each row is a player in the NBA. So each row and year are unique. So this first row is AC Green in 1991 year, and it has all of his per game stats for that season. So what we're going to do is we're going to use these per game stats, like 2-pointers made, 2-point percentage, etc., to predict how many points he would have won in the MVP voting. And in this case, he won 0 votes, but other players on his team, the Lakers, won votes. Magic Johnson won a lot of votes that year, 497 out of the 960 max. And what we're actually going to be predicting is this win share. So it's the percentage of MVP votes a player got in a given year. All right, so with that look at the data, let's go ahead and dive in. And the first thing we're going to do is we're going to import pandas as PD. And let's go ahead and run that. And then we'll go ahead and actually read our data in using pandas. And the file is called playermvpstats.csv. There are links in the description if you want to download this particular file and work with it yourself. So let's take a quick look at stats, and we can see it's the exact same file we just saw in the CSV browser. Each row is a player, and it goes from 1991 all the way through to 2021. You can't see the year here, but we have data for all of those years. All right, so we need to do a little bit of data cleaning before we can actually do some machine learning. Don't worry, it's not a lot, but data cleaning is really important, and you'll need to do it regardless of what data science work you're doing. So let's first go ahead and delete this column called unnamed 0. It's not really doing much for us. So we just do that using del and 0. So let's go ahead and do that. So that column is now deleted. The second thing we can do is machine learning algorithms usually don't like null values, missing values in your data. So some algorithms will work with missing values, but most won't, and the ones we're going to use today won't. So let's go ahead and actually figure out if we have any missing data in our CSV file, which is now read into the data frame stats. So the way we do that is we use this isNull method in pandas, and we call it on the stats data frame. So let's go ahead and do this, and this returns a bunch of true falses. It's true if it is missing or null, and it's false if it isn't. So you can see most of the values are false. To make it a little bit easier to read, let's call the sum method on this. And what sum does is it goes through every single column and it adds up all the true values. So if there are no nulls in a column, it's going to show 0. But if there are nulls, it'll show the number of nulls in that column. So you can see there are 50 null values in the field goal percentage column, 2,042 in the 3-point percentage column, and so on. So all of the null values are in these percentage columns, which makes me suspect that this missing value actually means that the person didn't attempt any 3-pointers. Because 3-point percentage is the number of 3-pointers you made, which is 3p, over the number you attempted. But if the number you attempted is 0, then the percentage would just be missing because it wouldn't be a number. So let's see if we can validate this hypothesis by checking to see in the cases where the 3-point percentage is null, how many 3-pointers were actually attempted. And the way we can do that is we can say, so we again use isNull, and then we look at the 3-point percentage column in cases when it is null. So what this will do is select any row in stats where the 3-point percentage column is null. So we can see there's quite a few rows here. But to make this a little bit simpler, let's only look at a couple of columns. Let's only look at the player and the 3 pointers attempted column. All right, so let's run that. All right, so we can see here, this is a lot easier to read, and we can see when the 3-point percentage is null, in all of these cases, it meant that the 3 pointers attempted were 0. Let's do the same thing real quick just to verify for the free throw percentage. So I'll just modify this to look at free throws attempted and free throw percentage. And we can see it's the same. So any player or all of these players who had undefined or missing values for free throw percentage had 0 free throws attempted. So we'll just go ahead and replace all of these missing percentages with 0. It's not technically correct, but it's good enough for what we're doing right now. And to do that, we'll just use the fill NA command. So what this says is look through the stats data frame, find any missing values or null values, and replace them with 0. So it's not technically correct to say that someone who attempted 0 3-pointers has a 0% 3-point percentage, but for our purposes, it's okay, because if you attempted 0 3-pointers, you're probably not in the MVP race anyways. So it's not going to make a huge difference for our predictions. But something to be aware of when you're replacing missing values, and just think about if it's important to what you're actually predicting or not. All right, so the next thing we're going to do is actually create our first attempt at a machine learning algorithm. And to do that, first let's take a look at the columns and see which columns we want to use to make predictions. So in this case, we'll be using all of the numeric columns to make our predictions. So we'll create a list called predictors, and we will put all of the numeric columns into it. So I like being really explicit with predictors because it really helps when you are actually making your predictions to know explicitly what the list is. So you don't accidentally have something in your predictors that you shouldn't, or you're not accidentally missing something that you should, etc. It just makes it really clear when you make this list of your predictors. So we're not going to use player or position because those are strings. We're not going to use team because that's a string, or team. TM is the abbreviation, team is the actual team name. But all of the other items here are actually numbers, and they're okay to use in our prediction, except these. So if we use these, then the algorithm will actually know what we're trying to predict. And we only want to use things that don't give the algorithm direct information about what we're trying to predict. And in this case, the share, so the percentage of MVP votes you won, is exactly what we're trying to predict. So we'll get rid of this. Points won is very highly correlated with share, because share is just the points we won divided by the points max, and that's what we're trying to predict. So let's get rid of that. And then points max we'll also get rid of. So in this exercise, we are trying to predict the percentage share of MVP votes that someone got in a given year. And if we go to our CSV browser, you can see that on the right. You may have seen it earlier, but basically this is just the points won divided by the points max. And because of how we cleaned the data earlier, some rows where people didn't win MVP, the points max is listed as 0. Not technically correct, but it's okay because we only care about the share column, and the share column is accurate. They actually did get 0% of the MVP vote. So remember that we're trying to predict share, and we want to remove any variables that directly correlate with share, because those are the things we're actually trying to predict. We don't want to put them in our predictors because that will cause the algorithm to overfit. And I'll talk a little bit more about overfitting later. All right, so those are our predictors. That's what we're going to use to predict the percentage share that someone got of the MVP vote. So now let's set up our training and testing data frames. We'll use our training data frame to train a machine learning model on, and then we'll make predictions on the test data frame. So for train, we'll basically take anything before 2021. So we'll just say stats year is less than 2021. So this gives us all the MVP data and all the player data from before the year 2021. And then our test data will be 2021. So our data is actually temporal in nature. We have MVP voting data from 1991 through 2021. So you have to be really careful in a case like this, not to test on data that is before data you're training on. For example, you don't want to train on data from 1995 through 2021 and then make predictions on 1994, because that's information the algorithm wouldn't have had if it was running in the real world. In the real world, we would use this algorithm at the end of every season. So at the end of a season, we would say, okay, let's look at our season statistics, and then let's think about who we're going to predict is MVP. Now, you're not going to have data from future seasons at that point, right? When you're predicting the MVP for the 2022 season, you don't have data from 2023 and 2024. So we want to make sure the way we test the algorithm is the same as the way we would use the algorithm in the real world. That's so important. And when you have time series data, be really, really careful not to use data from after your test set when you're training the algorithm and making predictions. Really, really easy to cause that issue. And if you do, you'll overfit. And what that means is your algorithm will look awesome when you're testing it, look incredible. And then when you go to actually use it, it'll turn out that the algorithm doesn't work at all. And you do not want to find out at that point that the algorithm doesn't work. You want to find it out when you're testing your algorithm. All right, so let's keep going. So that's our training set and our test set. And we will use a fairly straightforward model to actually create our first machine learning set of predictions here. We're going to use something called Ridge Regression. So you're probably familiar with linear regression, where you make predictions based on drawing a line through the data. Ridge regression is a form of linear regression that is designed to prevent overfitting. So we're not going to get too deep into it now, but basically ridge regression shrinks the linear regression coefficients to avoid overfitting. So we're going to go ahead and just create that model. So basically what we did here is we imported a ridge regression model from scikit-learn. Make sure you have scikit-learn installed. And then we initialized the ridge regression model with an alpha of 0.1. And alpha just controls how much the coefficient is going to be shrunk to prevent overfitting. So feel free to play around with different alpha values if you want to see how performance changes when you're training it versus testing it. All right, so now we can actually go ahead and make our first set of predictions. So let's go ahead and just fit the model first. Got ahead of myself here. So let's fit the model, and we will fit it on all of the predictor columns in the training data set. So basically, we're taking all of these columns in the training data set and making predictions based on them. And what we're trying to predict is share. So this is saying use all of these columns and predictors to try to predict the share of an MVP vote that someone got. So let's run that. And now we can actually go ahead and make predictions. So what we'll say is predictions is, and again, we're using the predictor columns in the test data frame to actually make these predictions. So let's go ahead and run that. And let's take a quick look at predictions, see what it is. So this is just a NumPy array. We're actually going to convert it to a pandas data frame because that just makes it a little bit easier to work with and makes it print out a lot nicer, so we don't have to deal with looking at the array. And what we'll say is our column name here is just going to be called predictions. And we will have the same index as our test data. All right, now let's take a look at predictions. So you can see the index column on the left. That's the same index as we had for our test data. And then you can see the predictions. All right, so what we can do now is actually compare our actual values to our predictions. So let's go ahead and combine these two data frames. And we'll use the concat method to do that. It combines two pandas series or data frames. And what we'll combine is test, and we'll combine the player and share columns because we don't need to look at all the other columns at the moment. And we will also concatenate the predictions that we just made. And we will concatenate them on axis 1, which means we will combine the columns. So let's go ahead and do that. Take a look at combination. So you can see we basically added an extra column here, predictions, which pulled from this data frame that we just created. So we now have this combination data frame. And for every player, it now, in the 2021 season, which was our test set, it now has the share, which is the actual percentage of the MVP vote they won, and then our predictions. All right, this is a little bit hard to look at right now because we only really care about the MVP winners. We don't care about people who didn't get any votes, unfortunately. Sorry, Aaron Gordon. But let's go ahead and just sort this data frame so we can see the people who won MVP first. And let's just take a look at the first 10 rows here. All right. So we can see Nikola Jokic won MVP. He does not have the highest predicted amount, though. That would be Giannis Antetokounmpo. I think this is the highest across all of the players, the highest prediction, but we can't be sure, right? It's really hard to tell the rank order that someone was predicted to finish in the MVP voting, and that's really what we care about. We don't care as much about the absolute values, right? So Giannis was predicted 0.207, but that doesn't really matter to us. What we want the algorithm to say is Giannis will finish 4th in the MVP voting. So let's actually look at the rank in a little bit. But before we do that, let's actually think about an error metric and think about how do we actually evaluate if this algorithm did a good job. And this is one of the most important parts of your machine learning project is picking an error metric. The most important part is setting it up and making sure the way you set it up makes sense in the real world. And we talked a little bit about that, making sure we split our training and test setup properly. Now, the error metric helps you know if the algorithm did well or not. So let's try a default error metric from scikit-learn called mean squared error. This is a really common error metric that's used in regression tasks, which is what we just did. Regression is when you're predicting a continuous number. And let's just see if this makes sense for us. And basically, this mean squared error function takes the actual values and the predicted values, and it comes up with an error metric based on that. All right, let's run that. So we can see our error metric is 0.00266. And basically what this is saying is this is the mean difference between the actual prediction, between the prediction and the actual value. So it subtracts the actual value from the prediction, squares it, adds them all together. But this isn't super meaningful to us because we don't care about the actual values, 1. And then 2, a lot of the values are actually just 0. So let's take a look at this. So we can see out of all of the share values, the vast majority of them, 525 of them, are actually just 0 because those folks did not get any MVP votes. Most players in the NBA each season don't get any MVP votes. 99% or so don't get any MVP votes. So this error metric doesn't make much sense for us because if we improve our performance at predicting who finishes 100 through 150, it doesn't really matter. We just care about the top players, the top 5 MVP vote getters. So we need a new error metric, one that actually thinks about the rank of the player. So as we do that, we'll actually go ahead and just figure out the ranks different players got. So to do that, we can go ahead and sort this combination data frame on the actual share of votes people got. I'll again just type out ascending equals false because we want this to be in descending order. All right. So what we can do here is actually go ahead and assign a rank to this. So let's go ahead and just assign a rank column. So we've sorted this in order where the highest row has the highest vote share and the row furthest down has 0 vote share. So we can actually make a rank column that uses this to assign a rank. All right, and I started my range at 1, so I need to add 1 here in order to account for the number of rows we have. So let's actually take a look at combination, the first 10 rows, and see what's going on. So we can see we now have a rank of basically in order of MVP voting, what the rank was. So we can see Nikola Jokic was rank 1, Joel Embiid was rank 2, and so on. Now what we need to do is figure out the rank for our predictions. So let's sort combination in a slightly different way. We'll sort based on the predictions. I think predictions was the name of the column. Yes, it was. So we'll sort it on predictions, and we'll say ascending equals false. And now we can assign a predicted rank column using the same technique we just did. All right, and now let's take a look at combination. So we can see we predicted that Giannis Antetokounmpo would win MVP, but he actually ranked 4th. Joel Embiid, we predicted 2nd, was 2nd. Jokic, we predicted 3rd, was 1st, and so on. So you can see the difference between our predicted rank and the actual rank. There's some big outliers here, as you can see. All right, so what we actually need to do here is figure out what our error metric should be. And there are a variety of directions you could go here, but I think one that makes sense is, of the top 5 people in the MVP race, how many of them did we correctly place in the top 5? So if you're a top 5 vote getter, did our predictions also place you in the top 5? Because what we really care about is, did we correctly predict all of the people in the top 5? So let's go ahead and create an error metric that can do that for us. And the metric we're going to use is called average precision. It's not a very commonly used error metric for this type of task, for a regression machine learning algorithm, because it deals with ranking. But this is an interesting problem because there is ranking involved. Let me actually sort this a different way so we can see it more easily. Okay, so what we're trying to figure out is, of the top 5 ranked players in the MVP voting, how far down do you have to go in our predictions to find them? So for Nikola Jokic, you just have to go down 3 predictions. For Joel Embiid, you have to go down 2. For Steph Curry, you have to go down 6, and so on. So basically what we're going to say is, did you have the person who is supposed to be in the top 5 in the top 5? If so, great. We're going to give you a perfect score. If you didn't, we're going to see how long it took you to actually include that person and penalize you based on how long it took you to actually predict that person in order. So we would be heavily penalized here, our algorithm for Chris Paul, because it took us 33 tries to actually guess that he was in the top 5. All right, so I'm gonna go ahead and write this out so you can actually see what the logic looks like. So we're gonna create a function called findAP, and we're gonna take a data frame. So what we'll say is, we'll do the same thing we did before. We'll actually sort by the, let me find this. We'll sort by the share to find the actual winners, and we'll take the top 5. So what this is saying is sort the data frame by share, and then take the top 5 MVP winners, because those are the folks we want to see how well we predicted. And then what we're going to say is we're going to take a look at all of our predictions and sort them. All right? And then what we'll say is we will initialize found and see. And we'll just go down our predictions, and we will keep count of how many of the top 5 MVPs we found and how many total records we've seen. So for example, this is sorted by predictor. So we go to our first row, we found Giannis, he is top 5. So we give ourselves a point for that. Then we find Joel Embiid, he's also top 5, so we give ourselves a point for that. Then we find Nikola Jokic, he's also top 5, we give ourselves a point for that. Then we find Luka Doncic, who is not in the top 5, then LeBron James. Then we find Steph Curry, so we give ourselves a point, but we penalize ourselves because Steph Curry was not in our predicted top 5. And then so on. So I'm going to write this out, and hopefully it becomes a little bit more clear how this actually works. So we'll iterate through all the rows in predicted. And what we'll do is we'll say, hey, if the player in this row is in our actual top 5, what we'll do is we'll increment our found counter. And then what we'll say is we'll give ourselves credit for finding them. All right, and if we didn't find them, we increment the seen counter. All right, and then what I'll do is I'll return, okay, so let's say find AP for combination. We have to type .values because we only want to look in the values in this player column. So let's run that. All right, so we can see it looks similar to the manual process I walked you through. So we're looking through the predicted data frame, row by row. It's sorted in order of predictions. So the first 3, we got 1s on, perfect scores. The next one, we got not perfect scores on. So we got a 4 out of 6 here, which is 0.666 for Steph Curry, because it took us 6 tries to find him. And we already found 3 other folks. So that's 4 positives in 6 tries. So 4 out of 6. And then we have to go way down. So all the way to row 33 to find Chris Paul in our predictions. So here we get 5. So we found all 5 MVPs, but it took us 33 tries. So that's 5 out of 33. So that's what you're seeing here. And what we need to do is actually just aggregate these. So find the sum divided by the length to actually get our error metric. So our error metric here is 0.76. And that means, so a 1 would be perfect. In our first 5 predictions were all the actual MVPs. So the lower this gets, the longer it actually took our predictions to find the correct MVPs. So we want this to be as high as possible. All right, so this is a good error metric because it actually helps us predict the top 5, which is what we care about. You could have gone other directions with this error metric and they could have been perfectly fine error metrics, but just make sure you can justify your error metric with the real world. All right, so we now have a way to find our error. So let's go ahead and actually run this for all of our years now. So you notice we only made predictions for a single year. We can actually go ahead and use a principle called backtesting to make predictions for most of our years. So we'll actually write a loop and we'll say for year in years, and we'll start with the 5th year in our data because we need some data to make predictions with before we actually start making predictions. So what we'll do is we'll split up the train set and we'll say any rows with the year less than year are training data. And then the row where the year equals year is our test set. So basically what we're doing is we're looping through our years. We're starting at year 5, which is, so we're starting at 1996. And what we're saying is all the data from 1991 through 1995 inclusive becomes our training set. 1996 is our test set, which we're making predictions on. That's the first iteration through the loop. Second iteration through the loop, year is going to equal 1997. So anything before 1997 is the training set, and then 1997 is the test set, and so on. And this will let us make predictions for every year from 1996 through 2021. This is good because it makes our error metric more robust. If we only look at error for a single year, that year could have been really weird, right? There could have been something going on with the MVP voting, and even if our algorithm looks good, that doesn't necessarily mean that we have a good algorithm. So the more years we can test our algorithm on, the more confidence we can have that it's not going to overfit and that it's actually going to work properly in the real world. All right, so let's go ahead and finish this off. This is a principle called backtesting in stock prediction that we're applying here. And this is just the same code we used before to train the model. All right, so we basically split up our data into training and testing sets. Now we're fitting the model, and then we're going to make predictions. I'll just copy and paste some of the boilerplate code from before, so you don't have to watch me type it out again. So then we make predictions using our model. Then we make the predictions into a data frame and combine it with the actual data. Then we're going to append to all predictions. So all predictions is going to be a list that has predictions from every single year. And then what we're going to do is we wrote this find average precision function, and we're just going to append that as well. So at the end of this loop, we will have all of our predictions in a list of data frames, and we'll have all of our average precision scores. All right, so let's go ahead and run that. And what we can do now is just calculate mean average precision, which is the sum of all of our average precisions divided by the length. So our mean average precision is 0.711. So our algorithm looks a little bit worse when we run it across all of our data, but still pretty accurate. We're generally finding the top 5 MVPs pretty quickly, is what this means. All right. Now, if we want to diagnose and debug a little bit more and dive a little bit deeper into our algorithm performance, we need to think about the ranks that we predicted and the actual ranks of the players in the MVP vote. So we're going to use a function called add ranks to actually add the ranks in so we can see them and just use them as diagnostics. And when you're diagnosing your machine learning algorithm and trying to improve it, you want to make sure you have good diagnostic info so you can actually dive in and think about why isn't this algorithm performing well? How could I improve it? Okay, so we're going to do something very similar to what we did before. If you'll remember here, we added the predicted rank based on how we sorted the data frame. So I'm just going to copy and paste this actually over. And yeah, let me just change the variable name so I don't have to change it later. Let me find the predictions as well. All right, so what we're doing here is similar to what we did before, but we're sorting the data frame by the actual share of the MVP vote someone got. We're adding in the rank. Then we're doing the same for predictions, and we're adding in the predicted rank. Now we can actually add in the difference between ranks. So all we do here is we say combination RK minus predicted rank. So what this tells us is the biggest difference between the actual rank and the predicted rank, which is gonna help us diagnose any errors we've made with, not errors, but anything we could improve with our algorithm. For example, if we notice that we're consistently misranking people who are in a certain position, we can think about, okay, what are their stats? What's their position? How do we add that information into our algorithm? So let's do that. And then I'll just show you an example of what this add ranks will do. Combinations. Sometimes I type an extra S, like I did there. All right, and sometimes I use the wrong variable name, like I did there. All right, let's go ahead and run that. So we can see this is our predictions for the 1997 season. And you can see it tells us, okay, what was the actual rank that someone got, and then what was our predicted rank, and what is the difference? And what we can do actually is just sort values by the difference to find people who had the biggest difference. I would need to put the sort values outside here. All right, so we can see the people who had the biggest difference between their actual rank and their predicted rank. Now, we don't care about people who were ranked below a certain threshold. So what we can do here is only look at people who had a rank of less than 5. So they were in the top 5 of the MVP voting. Now this would work. I would need to assign this to a variable. And then what we can do is do this. All right, so let's go ahead and run this. All right, so this gives us the top 5, or top 4 actually, because I did less than 5. So now the top 5 MVP vote getters in the 1997 season, along with their predicted rank and the difference. This is helpful for diagnostics. We're not going to use it at the moment, but we will use it later. So the next thing we're going to do is we'll build a backtesting function just to make it really easy for us to continuously run it and get predictions whenever we want, instead of copying and pasting that loop. So this function will just do what this code did, but in a nice function form. So let me just copy and paste this code down here, and then we'll rename this to account for some of our more generic variable names. Right, so that should work. And then there's a couple of things we'll do just to make our life easier later on. So let's add a return statement, which is necessary. But when we return, we're going to return the mean average precision, which is the average precision averaged over all the years. So that just gives us one metric we can look at to see how effective our machine learning algorithm was. And then we'll just concatenate all the predictions. All predictions is a list of data frames. We'll concatenate it into a single data frame just to make it easier to work with. And we will also use our add ranks function to add in the ranking columns to this combination data frame. All right, so now what we can do is we can just run on a single line all of this code. So we'll go ahead and backtest our regression model for all the years from year 1996 onwards, and we'll pass in our predictors also. So let's go ahead and run that. And we can see we got the same result as before, 7112, but we now have this nice function that we can call easily to test different models and different combinations of predictors. So it is really, really nice to have a single function you can call, because it just makes it easier to iterate, to add more predictors, take things away, change models, see what works, what doesn't. So try to have all of your prediction logic happen in an easy function if you can. All right, so now let's dig a little bit deeper into diagnostics, and I'll just copy and paste the bit of diagnostic code from before. So what this is doing is it's looking at all predictions, and it's looking at anyone who is ranked 5 or lower in the MVP, so 1, 2, 3, 4, 5, and then it'll look at the biggest differences, the 10 biggest differences. So we can see Jason Kidd was ranked 2 in the MVP voting, but we predicted him to be 52, Glenn Rice, Steve Nash, etc. And what we could do, we don't have time in this particular tutorial, but what you could do here is dig in a little bit deeper and look at Jason Kidd's stats and look at where does he differ from other MVP candidates and why would he be being misranked by the algorithm. Another thing we can do to diagnose our algorithm is we can look at the coefficients of the regression. So underscore here. So this tells you which variables the algorithm is keying in most on. The highest coefficients indicate the variables that are most important to the regression. Of course, this isn't super useful because you can't tell which columns are associated with what. So we actually need to turn this into a pandas series, and then we need to combine this with another pandas series, which would be the column names, which is the predictors in this case. So we can go ahead and concatenate those on axis 1, which means join the columns. And then let's actually run this and see what we get. And this is not super useful either because the values aren't in order. So let's actually go ahead and sort this on column 0. So let's go ahead and run that. All right, so we see the most important variable to the algorithm is effective field goal percentage, then defensive rebounds, then win-loss percentage, etc. So this can help you see, okay, which columns does the model think are important to MVP vote share and which columns does it think are not important. So that's one way to diagnose a regression model. All right, so to give the model a little bit more information, let's try adding some more predictors. So one thing we can do that's pretty easy is we can look at the ratios between the season averages for all the players, and we can look at a particular player. So for example, if you're triple the scoring average in a season, that might tell the algorithm something. So let's look at a few variables here. The reason I'm including year will become apparent in a moment. So we're going to group this by year. So basically what this is saying is take all of our stats, pull them apart into separate data frames, one for each year. And then in those data frames, we're going to apply a lambda function. So the mean method calculates the mean for each of these columns. So we're going to calculate the mean points scored per season, the mean assists scored per season, the mean steals, and then we are going to divide every player's average by the mean. So if a player was below the mean, you'll have point something, 0.1, 0.2. If the player's numbers were above the mean, you'd have 2, 3, 4 as your value. So let's go ahead and run that. And then just so you get a sense of what this looks like, this gives you the ratio between a player's stats and the average stats for that season. All right, and we can now add these to our stats data frame. All right. And these are just the column names that we're going to use in the stats data. We don't want year, so those are going to be the columns that we take. And then we are going to say we want to assign some of the values from stat ratios here. So that'll be these columns, except year. We don't want year. All right, so let's go ahead and run that. So if we look at stats now, we see on the right, we now have these extra columns added. So for AC Green, this is the ratio between his points scored per game and the average, and so on. You can see James Worthy scored a lot more points than the average. All right, so the next thing we can do is just go ahead and add these values to our predictors. So what we can say is this, predictors are now, we're adding those values in, and we can just copy and paste our prediction code from before, where we ran the backtest to see if we actually improve anything. So let's run that, and we can see we did improve a little bit on our error metric. So we went from 0.711 to 0.720. That means we're successfully getting a few more people into the top 5. We're getting them higher up in our predicted ranking. So people who actually won top 5, we're now predicting them a little bit higher up in our predicted ranking. All right, there's a couple other interesting variables we could try. So position is a string, but it's a categorical string. So your position in basketball, actually, let me just show you. Using .unique. So you can see these are the unique values in the position column. So they are strings, but they're categories too, right? Each player, several players have the same position. So what we can do is just code this as a numerical value. So we can turn this into a category and then get the category code, which will just turn it into a number. So let's just take a look and you can see what I'm talking about. So you can see this NPOS column here is now a set of numbers. All right, and we can do this all for another column also. We can do this for the team column. So some people in the NBA claim that which team you're on does not affect whether you're going to be voted MVP or not, but we can validate that. We can see if it's true or not. All right, so we can do the same thing there. The problem with this is these types of categories. So if we look at these types of categories are not ordered, right? So for example, the unique values in NTM are 7, 27, 14, 8. These all correspond to teams. So 7 might be the Lakers, 27 might be the Milwaukee Bucks, etc. But having a higher number doesn't really tell the algorithm anything, right? So typically for a regression algorithm, you need your predictors to follow some sort of linear relationship. Now there are ways to make that different, but it's very hard for a linear regression algorithm to pick up a categorical relationship. So we need to use a different kind of algorithm to get value from these predictors. And the type of algorithm we'll use is a random forest. So a random forest creates a series of decision trees and averages the predictions from those trees. So we can also import that from sklearn, which is amazing. And we can initialize the model like this, random forest regressor. And you have to pass in the number of individual decision trees you want to create. In this case, we're going to create 50. Just so it runs fast. You probably want to initialize more. I would recommend anything up to 500. Beyond 500, you'd probably see diminishing returns. I'll set the random state to 1. That just means if we run the same code twice, we'll get the same result. And min sample split. So in a decision tree, I won't go into a lot of detail here, but the model works by essentially creating a series of branches by splitting the data up and splitting them on specific columns. So min sample split says don't make a split unless there are a certain number of values in that node to be split. So the higher you set this, the more resistant the random forest is to overfitting and the faster it runs. The lower you set it, the more accurate it'll be, but the more risk that it'll overfit. So I'm going to set it to 5. You can feel free to experiment with different values if you're doing this on your own. Now the really nice thing about creating our backtesting function is all we need to do is replace that with RF. And the random forest model is going to take a while to run. So I'm not going to run it on as many years. Instead, I'm going to start at year 28, which I think is 2020. Let's take a look. 2019. So I'm going to start at 2019. So it'll only make predictions for 3 years. All right, let's go ahead and run that. And we can see what the error is from that. And while we do that, if we want to compare this against our regression model, we need to run our regression model only for these years. So let's go ahead and also do that so we can compare apples to apples here. All right, this will take a little bit to run. As I mentioned, random forests run more slowly than linear regression models, just because of the internal math and the way they work. But it shouldn't take too long. It should finish up quickly. So while we wait for these results, we're coming close to the end here. So I want to summarize what we did. We took a CSV file, we read it in, we did some data cleaning to get it ready for machine learning. We split the data up. So I'm going to scroll up here to what we did at what time. We split the data into train and test sets. We created an initial machine learning model, and we looked at our initial predictions. Then we did some diagnostics to figure out what a good error metric should be. And we eventually ended up with average precision and mean average precision as that error metric. Then we used that to create a backtesting model that could test across several years. So train and test on several different years. And we used that to get a single error metric for all of those years. Then we did some diagnostics just to dig into which columns are the most used by the model, how could we improve performance. And if you want to look at next steps, this is a really good place to do it. Look at the difference between the rank and the predicted rank, and then dig more into those player stats to see where the gap is. All right, then we added a few more predictors, which had a little bit of impact on our accuracy. And then we played around with a different algorithm, a random forest algorithm. And we are waiting now to see what the error from that random forest is. So if you want to try this on your own, there's a few steps you can try as next steps after the steps that I've just showed you. So the first and most interesting one is doing a little more investigation to figure out what you could add, what you could take away, potentially even find other data sources of other publicly available data that you could add in here to create better predictions. That's one. Two, you could generate more predictors within the set. So I showed you how to generate some additional predictors. There's a lot more you could generate here. You could play around with different machine learning models. So you could try a neural network. You could try other more complicated algorithms. And finally, what you could do is try just getting more data from the original source. So this data came from Basketball Reference. I only went back to 1991, but you could go back even further and see if you have more data and you make your predictions for a longer period of time, if that changes anything. All right, so this finished running. You can see that our random forest was more accurate than our linear model. So I will leave you with that. Hopefully you have a good idea of how to build this project out and what the next steps are now. And thank you for watching, and I hope it was helpful.